Okay, once again, thank you all for coming to the Getting Started with Spatial Research workshop. My name is Yoh. I work for the UCLA Office of Advanced Research Computing, and I'm also on faculty in urban planning. So I don't know if there's any urban planners out there, but welcome. And in the digital humanities as well, where I teach spatial data science. So the workshop today is both for, I would say, for beginners as well as intermediate, researchers who want to learn more about spatial science, getting started, like how do you get started with actually doing GIS and spatial research. So the first thing I'm going to do is I'm going to post this website for our workshop in the chat here. So this is our home base for today. So if you guys could go to the link that I have posted there, and I'm going to start sharing my screen so we are on the same page. So let me get that started as well. And let me move things around. Okay. And what I'm going to do is I am mostly going to be talking about my shared screen and also kind of glancing at the chat window, which is on my other screen. But for some reason, if something happens, you can't hear me, or you have a question, or I'm unclear, I'm going too fast, and I'm not checking the chat room, please feel free to unmute yourself and let me know. Yeah, and I'm also very, very curious to know about you and about your research. So please feel free to have an active chat going on while the instruction goes on. Okay, so let's get started. The first thing I'd like you to do before I even talk about GIS and spatial research is if you scroll down here, there's a link to a Jupyter Hub. And if you guys could go ahead and click on that link, and what it would do, let me see if I can mimic this for you, is it should come to a login screen that looks like this with an orange button. Click on the orange button. And when you see this drop down to select a provider, you want to choose UCLA if you're from UCLA. And a quick way to do that is to just type UCLA in that search box, and it'll be the first item that shows up. Or you can scroll and find UCLA, University of California, LA, and then hit the log on button. And you should be familiar with this whole process. Type in your logon ID, have your cell phones ready so that you can do this whole thing, UCLA authentication. And let me do that with you guys. And what this whole process is doing is that it's now pulling the class material that I have prepared for today. That includes what's called a Jupyter Notebook with a whole bunch of Python code, my lecture notes, it includes data. Everything that we're going to cover today is being pulled into this environment called Jupyter Hub. And Jupyter Hub is a server that sits somewhere in our data servers here at UCLA. And it's hosting a cloud-based environment for coding. It allows you as a researcher here at UCLA to have a free account. So when you pulled this class content, you launched Jupyter Hub, it created an account for you if it was the first time you used Jupyter Hub. And it has allocated kind of a virtual machine for you to use for your research. And this is a free resource that we provide from OARC to the campus community. So you can use it even after this workshop, which is really cool. And now when you land on this page, it automatically, I've set it up so that it automatically lands so that I believe you should see this Intro to GIS notebook open in your Jupyter Hub. Okay, so if you're seeing something else, if you see an error, please chat it down on the chat room. Okay. And otherwise, I'm going to assume that we're on the same page here and that you see the entire lab here scrollable on your screen. And for those of you, if you had just joined, I'm going to repost the URL in the chat room. So from that URL, this is our home base. This is class website. Please scroll down to the Jupyter Hub link, which will ask you to authenticate yourself. Choose UCLA from the dropdown of campuses that you belong to, and then authenticate yourself and go into the Jupyter Hub. If you're not from UCLA, I know there's a few of you who are not from UCLA, you won't be able to log in using the Jupyter Hub, which is linked to the UCLA two-factor authentication system. I have an alternative here called a binder link, of which you can click. And what this will do is that this will launch a completely separate virtual environment, which is not affiliated with UCLA, but you should be able to do the entire workshop through this binder link as well. But anything that you do in the binder link is temporary and you won't be able to save your work. So for those of you using the UCLA Jupyter Hub, you'll be able to save your work, come back to it later today, tomorrow, a week later. As long as you're a UCLA student, you'll have access to this material. And you have access to build your own notebooks and research for your own research as well. Okay. Cool. Okay, so I don't see any problems in the chat. That's a really good sign. I'm going to assume then, okay, that everybody is with me here and you see this page on your screen. Is that right? Okay. Okay. So, yep, great. Thank you, Valerie. Okay. Now, what I want you to do is to stay on this screen and follow my workshop. Hold on a second. I'll answer that question in the chat. Follow the workshop from your Jupyter Hub page and just scrolling along the way. What I'm going to do is I'm going to go in what's an interactive presentation mode. So my screen is going to look slightly different from yours, but it has exactly the same material as what is on your screen. It's just that I have this fancy kind of presentation mode that I'll be going through. I'm going to pause for a second here because I see somebody has an error. So let me pause here. Chelsea, you see an internal server error. Is there anybody else who is seeing an error on their screen and not coming to this page here? Chelsea, can you explain your error a little bit more? Do you see a red bar on the screen or are you not able to log on?
Yeah, it's the log on portion. Once I get to the click here to sign in with CI log on, I first had the option to use the drop down and click UCLA, but now it's just saying 500 internal server error, failure to get username from CI log on.
Okay. That's a curious one.
But I can also connect with you afterward. I don't want to hold the class if I can.
I'm happy to talk to you afterwards.
Okay.
Maybe you can try a different browser and try it from start.
Yeah, let me do that. Thank you.
Thank you. All right, so let's get started with the workshop, and I'm going to go in my presentation mode. So once again, I'm going to just double check that the recording is happening. Okay, good. So once again, welcome to workshop, and let's get started with some spatial thoughts and research ideas. Okay, so introducing GIS. So what is GIS? I actually am not too fond of the word GIS because what does it mean? Typically the word GIS is known for it being geographic information systems, but there's also something called geographic information science. And I like to refer to GIS more in the science side rather than the system side. The system side is more kind of machine-based. The science side is more spatial thinking. And when I talk about GIS or spatial research, I love the word spatial And I love it more than GIS because GIS to me is more systematic. It's more kind of software based. It's the tool. It's not the human or the science part of it. So where are we in GIS? That's why I like the word GIS as in science more than I like systems. But in other words, when we think about GIS, I'd like us to think about the tools and as well as the thinking that goes behind it, the spatial thinking. And so this, graphic kind of illustrates the difference between the two. However, they're very strongly correlated. Okay, so when we do spatial research, we need data. And without good data, we cannot do good spatial research. And I highly encourage you, when you do your own research, to first make sure that you have data that can do the research you want to do. Because oftentimes you want to do research and then, you do a little bit of research about the data and you find out that there is no good data to answer the research questions that you want to do. And you put yourself in a kind of a bind, in a corner. So most important thing is that you know or have good data to start with. And that will allow you to do good spatial research. So what kind of data types are there in GIS research? Let me just mention a few, kind of the most common ones. We have shapefiles, which is a proprietary data format for GIS from a company called ESRI. And it actually consists of many files that make up one spatial layer. And these are called shapefiles. So there's typically 3 or more files that combined make up a shapefile. And then we have KML, which is a Google Earth standard. And that usually has a .kml or .kmz extension. Although I'm seeing fewer and fewer projects that use KML because Google Earth has kind of been deprecated. So that environment is slowly kind of going away. And then we have GeoJSON. This JSON stands for JavaScript Object Notation. And it's a very kind of open standard for spatial data. And it follows kind of this JavaScript notation. It starts with curly brackets, and it's all just text. And then it has coordinates, and it has properties. And you can do lines, points, and polygons with GeoJSON files. I'm going to cover this a little bit as well. And then we have image files. You might be surprised to know that images can be spatial. Because when we talk about raster data, and I'll talk a little bit about that as well, these are imagery, like satellite imagery. That's why it's called imagery, because they're image files, essentially, and they can be JPEGs, PNGs, or TIFF files that we're perhaps familiar with. Non-spatial data is data that has no geographic information kind of embedded in it. So, Excel spreadsheets, comma, separated value files, CSVs, my favorite. JSON, not without the geo, so JSON, the JavaScript notation. And DBase files, this is kind of an archaic database format, DBFs. These are kind of an example of non-spatial data. Okay. And a lot of non-spatial data is used for what's called attributes. So if you have a data set of zip codes, census tracts, and then you have another separate table with a whole bunch of attributes, % black, % white, annual income, that kind of data, and then you want to link it back to spatial data, that's a strategy to make sure that you spatialize spreadsheets. Okay, so what's the correlation between spatial and non-spatial data? And the cool thing about this is that you can merge them, and there's strategies about bringing them together. Spatial data, you might get spatial data from a source like the county or local government or federal governments as a shapefile, and you're like, I don't need the shapefile, I just need the data. You can convert a shapefile into a spreadsheet and then get all the attributes from a shapefile. Vice versa, like I just spoke, non-spatial data. You have data as a CSV and it has addresses in it. You might be able to map addresses by doing a process called geocoding and assigning latitude and longitude coordinates to every single address in your spreadsheet. It might be a spreadsheet from a survey. You might work for public health in a hospital, and you have a list of patients and you need to map where they live, what zip code they're in. You can do a process called geocoding and map an entire spreadsheet of patients and then see their proximity to hospitals or so forth, right? So, you know, data is malleable. I love looking at data and then seeing the opportunities and the kind of hidden things that lie within the data and seeing whether or not we can spatialize it. Okay, so spatial data formats. Yeah, so we have typically vector data and raster data. So vector data, points, lines, polygons. You know, vector data, if you know like Illustrator or PowerPoint, all those elements that you can click and then you get these kind of corners that you can move, you can change the square into a rectangle, that kind of data, that's vector data. Drawing a line, click, 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 right? You're drawing a line, that's vector data. And so raster data is different. It's imagery. It's like a JPEG. It encompasses the entire surface. It drapes the entire surface. And every pixel, every little pixel, what's called a cell, has a value in it. So as you can see in these graphics, these are the same data. One is represented as a vector and the other is represented as a raster. So you can see how the same data can be represented differently depending on the data type that you're working with. For the purposes of this workshop, I'm mostly going to be in the vector world. If you're into remote sensing, climate change, environmental research, you might encounter raster data, like getting data from satellite imagery and processing that data. That's usually in the raster data world. For other kind of mapping inquiries, a lot of the data is in vector, like streets, building outlines, zoning, census data, all that kind of research is in the vector world. And that's what we're going to do today. Okay, so great. So I just kind of talked about vector data, points, lines, and polygons, and raster data, like digital photos. And, you know, raster data is often dictated by the resolution. You might have heard of, you know, for example, Landsat satellite imagery is a 30-meter resolution. What does that mean? 30-meter resolution? It means that a single pixel on your screen is 30 meters. A single cell of data is 30 meters wide, right? So that's, you know, half a football field. Or you might have heard of 6-inch resolution, right? Which means that you can zoom in all the way down to see, you know, a cell phone. So that's the differences between resolutions and raster data. Okay, so I'm an urban planner, and I know that not all of you are in the social sciences, but to get us started, I wanted to work on something that is relevant to any one of us as, you know, humans living in society. And so to get us started with spatial research, the topic today is going to be revolving around the social sciences, human geography, rather than the natural geography and physical geography. Let's talk a little bit about what that means. We're all familiar with this map, right? We're all a part of this process, being here in the United States. And so when we see a map on TV or in the newspaper or on our digital screens, there's a lot that goes behind the scenes to produce a map like this. So here's a map at the state level of our previous presidential election. And it's color coded by, you know, red or blue states by the election results. Now, it's summarized at what's called the state level. So it presumes that an entire state is a single color. But we all know that this is not true. However, it's been summarized at a higher scale. So it's been summarized at the state level. How does that happen? So we can look at the same map in a different kind of representation. And when we talk about different types of representations at different scales, that's called the geographic hierarchy. So like Aristotle said, the sum is the whole of its parts. So we know that that entire state of California is blue, but it's all summed from a single vote, all summed together to is essentially become a blue state. So we can look at different scales, right? So when we think about data and how to summarize data, aggregate data, we have to kind of think about, well, at what scale was the data collected? And at what scale does it make sense to publicize this data for research purposes or for the public to consume? So this is the same map. However, it's now split up by county. And it tells a very different story than as opposed to the state level map. And so when we compare the state level map to the county map, what's happening here? And this is an example of how we use geographic hierarchy to represent phenomenon in different scales. When we talk about the Census Bureau, which is the data that we're going to bring in today and in our hands-on portion, we talk about data that was collected at the individual level. And there's reasons why that data is not made available to the public, mostly for privacy reasons. And different data sets become available at different scales. So to protect privacy, the lowest scale is at the block group level. Here you can find statistics like population. And then when you get out to the census tract level, there's a lot more like income data, race data, and other variables become available to you. And you can map census data at any one of these scales because census data is hierarchical. You start at the block group, and then the block groups fall within a census tract. A census tract falls within a city, falls within a county, that falls within a state. So that is how this kind of hierarchy of geography works, and it works for a lot of data as well. Okay, so that's my kind of prelude to our hands-on portion of the workshop. I think we're all eager now to get started and get our feet wet, right? So unless, are there any questions so far? Any thoughts? Okay. All right, so let's get started. We're actually going to be coding together and producing outputs together in this environment. Let me go back to outside my presentation screen and go back to the screen that you should be seeing that looks like this. And let me explain a few things here and talk about Jupyter Hub, which is the environment that you're in. So this is Jupyter Hub. It's cloud-based. It's running on your laptop or your computer within your browser, right? So everything that you're going to do today works within a browser. So it's very computationally very light on your computer, which is great, right? Because in the past, when anybody did GIS research, you had to download huge software packages like QGIS or ArcGIS. And you have to install that package on your computer, and then you have to bring in all your data locally. Your data could be 100 megabytes big, some data is like gigabytes big, and then it uses tremendous amounts of resources on your local computer. So you needed a high-end computer to do GIS work. Now, this Jupyter Hub environment is in the cloud. And you're given, it's kind of like a Google Docs. And you're given this space as a researcher here at UCLA that you can use for your own spatial research. Well, not spatial research, any research that you want to do. It doesn't have to be spatial. It could be statistics. It could be any kind of coding, Python work that you want to do. Or R. There's also an R engine within Jupyter Hub. What you see on the left here, you should see a folder, Workshop Census. That is all the material. If I go back to the original home base from GitHub, I posted all my material for this workshop on GitHub. So I'm not sure how many of you guys are familiar with GitHub, but GitHub is kind of a public facing repository for projects in code. And so anybody can create a free account on GitHub, and you can upload, code, essentially HTML. Doesn't have to be code, data, JavaScript, Python, R, and it's a place for you to save your work and publish your work. And it has something called versioning. So anytime you upload something like code, and then you make changes to it, and then you commit those changes to GitHub, the record of changes remain on GitHub, which is great. This allows you to then, if you make a mistake, to go back and redo your work. So anyways, it's an environment that academics are beginning to use more and more. And even in the classroom, a lot of students are starting to use GitHub to save their work and produce research. So when you clicked on that link from my GitHub repo, it automatically brought in every single file from that repo into the Jupyter Hub. But if you go up one folder, you see this folder here, right? This is the root of your Jupyter Hub space. You should see that last folder here, workshop-census, because that's what you brought in. I don't think you see anything else there if it was the first time you logged in. But this is your space. You can create your own content here. So just to let you know, for your own research, that you might want to use this space after the workshop. Clicking again into the workshop folder that we're in, you should see the Intro to GIS notebook, IP, Y, and D. That should be on the screen right now. And you should, this is what I just talked about spatial data formats. All my stuff is in here. And eventually, we're going to run into some code cells. Okay. Just to let you know, when you run into a cell that looks like this one right here, right? This is the first code cell. You'll notice it because it has a gray outline around it, and it has what looks like code inside of it. This is what's called a code cell within your Jupyter Notebook. This whole thing here, IPYNV, is an IPython NV stands for notebook. It's a notebook because it actually operates like a physical notebook. You jot down notes, and then you can actually type in code and execute code within the notebook. So the idea of a Jupyter Notebook is that it's a new way of coding. It's new, interactive. It allows you to write notes, bring in images, provide links, descriptions about what you're going to do in your research, and then actually do the research itself within that same notebook. And you don't have to compile it and take it somewhere else. You can do it within the notebook, which is very, very powerful. So when you share your research to your teammate or to your professor or to a publication, if you can publish it as a Jupyter Notebook, it's very engaging, it's dynamic, it's interactive, and it can be beautiful. So how do you execute code in a Jupyter Notebook? When you see a cell that looks like a cell code, right, with the gray box, what you have to do is select the cell. You can actually see that you can change this code. I don't recommend you to change the code right now, but you can if you wanted to. Please don't at the moment, okay? I don't want you to change any code right now. But you'll notice that a blue bar is on the left. That means that this cell is active. I can also, if the cursor is in it, that means you're in what's called edit mode. That means you can edit this code. You can click outside of it, and it's not in edit mode anymore. There isn't a cursor in there, but you still see the blue bar. That means that this cell is selected. Whether or not it is in select mode or in edit mode, in order to execute this code, I want us to do this together, is to highlight this cell or be in edit mode or in command mode and do a shift. Okay, so hold on the shift button and enter on your keyboard. And what will happen is that cell will be executed. How do you know it was executed? You notice the number here on the left, right to the left of the cell has turned from an empty square brackets and it should have a number in there now. And for me, it's number 1. That number indicates that the cell was executed, first of all. If there's a number in there, it means it was executed. And that number indicates how many, the sequence of cells that you have executed. So it was the first cell that I executed in my notebook. That's why it's a number 1. If I were then to highlight this cell again and hit Shift Enter, I just want to run it again for whatever reason. I run it again and it executes, right? Shift Enter executes the cell. And now it has the number 2 in it. That means it was the second thing I've done on my Jupyter Notebook. Okay, so hopefully that kind of makes sense. And the fact that you're executing code directly in your notebook is pretty cool. This is Python code. What it's doing is that it's going to what's called a Python kernel that sits on a computer in the cloud that does the Python work for you. It's not happening in your local machine. And then it returns the results immediately after you execute the code into your browser. So that's the beauty of this environment that we're using. Oops. And I'll just go forward with that. Okay, so hopefully that gets us on the same page in terms of moving forward. Go ahead and execute that first code. But I'm going to go back and talk a little bit about what we're going to be doing next. So Python, I know. Yes, is there a question?
Yes, I apologize for interrupting you.
No problem.
When I did the enter, the shift enter, the brackets appeared, but there were no numbers. And so I went back and tried to do it again. And so I have brackets, but
Okay.
there's no numbers within. So I don't know what that means.
Okay. So first of all, do you see the blue bar next to it? That means that
Yeah.
this cell has been highlighted.
Yes.
And are you in the import GeoPandas cell?
Yes. Mm-hmm.
And then with that highlighted, and if you hit Shift and Enter,
Mm-hmm.
does it not execute that code and put a number in those square brackets?
No, like I said, the brackets appeared, but there was no number.
Okay.
And then when I'm looking down, I see brackets all along the data. Yeah, I don't know what it did. I just did the Shift Enter. Then I tried it again. So I don't know. I don't know. Yeah.
Is it Sonia?
Yes.
Sonia, I'll be around after class.
Sounds good. Okay.
Please stick around so I can help you with that.
Sure.
And anybody else who's having issues, I'll stick around afterwards and we'll make sure that we get it to work.
Thank you.
Sure. Okay, so let me go back. So let's talk a little bit about Python and census data. What we're going to do, and even though you're beginners with Python, I'm going to go right into the heart of kind of Python coding, knowing that you can execute these cells on your own and come back to the material and do it over and over again. So what I'm going to do is I'm going to kind of cover a lot of things in a short amount of time so that we can actually go through the whole process of getting data, massaging data, cleaning up data, querying data, creating maps with that data, and eventually publishing the data. So there's a lot to cover here. And I might be going a little kind of faster than you might want, but I want us to leave today with a whole spectrum of possibilities for you to be able to explore later. So that's kind of my tactic here, and hopefully it works. All right, so what we're going to do is we're going to, well, find census data. We're going to use a Python library called Geopandas. And a library is, you know, the beauty about Python is that you don't have to write all the code yourself. Other people have written what's called libraries and modules that you can bring in with one line of code. You can bring in an entire library into your Python notebook. And then all of a sudden, you are empowered with abilities to do things. For example, the one we're going to use today a lot is called the Geopandas library. Let's take a look at what that looks like. This is the home of Geopandas, which is a Python library that, again, you can bring into your notebooks with one line of code. And this is the outputs that it can produce. So this is the example gallery. Just look at all this stuff. We have raster data here, a lot of vector data stuff, global data with points on it. This is called a choropleth map. This is what we're going to work on today. And these are the types of outputs that you can do with this Geopandas library. And there are thousands of libraries out there. Okay. Where do you get census data? Okay, as a social scientist, getting census data is paramount. We need to be able to work with the Census Bureau, how to get their data, and how to bring it in. I have links here to directly go to the Census Bureau website, which, well, if you can navigate it and get data from them, kudos to you. It's not the easiest site to use. I have another resource here called Social Explorer, which if you're a UCLA student, you have access to with a full license to it. And you're free to explore this on your own. But what I'm going to do today is I'm going to use this website called censusreporter.org. I just want to quickly show you what this site looks like. You know, it has search engine. And what I like about this site is that it's very instant. So if I wanted to look up race, I can type in the word race. And you can see all the different census variables that show up for that query. I can click on one of these variables, Hispanic or Latino origin by race. And they have a lot of information here about how the census operates. So when I look at, you know, my topic might be race and Hispanic origin. What does that mean? I can actually go to their documentation. I can click on, you know, this image is the actual survey that we filled out a few years ago to populate the census data, right? So, you know, as we all know, we live in LA. Most of us live in LA. The question of Hispanic origin is complicated, but it's very important because 50% of the population in LA is Hispanic. So that's the topic that I chose for today's workshop. And I have already kind of preloaded the data folder in our workshop with census data. I talked a little bit about libraries. We're going to use these 3 libraries in our workshop today. Geopandas. So this code that you have already executed. Okay, I'm going to execute it again. I see the number 4 now. It's the 4th cell I've executed. Indicates that we've brought in these 4 libraries into our Jupyter Notebook. That's pretty cool. So now we are empowered with Geopandas. So anything that you see here, right, about how to create these beautiful maps and, you know, are available to us. That's what it means. It's available to us within our notebook. We're also bringing in a library called Contextily. Not that important to know much about it other than it allows us to bring in a base map. When we publish our map, we want to have a base map underneath our data so that we, as a reference, you know, boundaries of countries and so forth. So that's just kind of icing on the cake, I would say, kind of a library. And then in terms of plots, we're going to be making plots. We're going to use a library called matplotlib, which is one of the most popular plotting and charting libraries in Python. So these are 3 libraries that we're going to work with today. Okay. All right, so in terms of importing data, I talked a little bit about spatial data formats. The one that we're going to use today is one called GeoJSON. And let me talk about data formats. And GeoJSON is, I would say, one of the rising stars in spatial research because it's a format for spatial data that's actually has a small footprint, and it's pretty simple if you kind of get under the hood. And let me explain what I mean by that. The syntax of a GeoJSON looks like this. So if you've ever seen JavaScript or coded in Python, this might look really complicated. But when you kind of dig through the weeds a little bit, you'll notice a couple of things. There's a whole bunch of notations here, and this is called JavaScript notation. This starts with a squiggly bracket. when it starts with a squiggly bracket, you can be ensured that at the very end, it ends with a squiggly bracket. And then you have, things like this is the type. What type of data is this? It's a feature collection. Colon separates it, comma, features, and so forth. Then you have things, numeric values here. Hey, these are paired numbers, coordinates. Remember your XY graph in high school math, right? These are just coordinates, right? Coordinates on a Cartesian plane. So this is coordinates 102, 0.5. More coordinates here, multiple coordinates connecting the dots, right? Dot, 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 dot. That's a line. So that's what spatial data really looks like. It's a lot of either points, lines, or polygons. And the way that that data is stored in either in a database or a file typically will look like this. If it's a point, it's just a pair of coordinates. If it's a line, it's an array of pairs of coordinates. If it's a polygon, it's kind of like a line, but it has a knowledge to connect the last dot to the first dot, right? So it kind of full circle, and so forth. So hopefully, it kind of debunks a little bit about the GIS data formats and the vector data that we're going to be using is actually not that complicated under the hood. And okay, to make my case, I'm going to introduce you to a really, really cool resource for creating your own data and previewing data that you might have downloaded from somewhere else. It's called GeoJSON.io. And it's an open source project where you can actually start with a world map. I can zoom in, right? This is pretty awesome. Very kind of Google Maps-esque. Here we are at UCLA, or here I am at UCLA. Oops, over here. And I happen to be in the Math Sciences building right now in my office. And this website allows you to create data. So if I click on this icon here, this is a point. I can actually, this is exactly where I am. I'm going to hit my head with this icon right now. And the moment I click, it creates data. It creates spatial data. So this is the GeoJSON notation syntax for that point on the map. This syntax I can use, save it as a GeoJSON file, and I can load it to Google Maps. I can load it to any kind of GIS application, and it will produce this point on my head in the technology sandbox on any other mapping platform because it's interoperable. Right? So I can actually create, maybe one of you is an engineer and you're in the building next to me. I'm going to put a point on your head, and now I have 2 points in my GeoJSON. Same thing, right? I can do a polygon. Can I? Yeah, I can draw a polygon. And it creates the spatial data for that polygon. So that's how spatial data works. And this is what we're going to use for the lab today. Okay, so there's no magic in terms of how this data is put together. Okay, so now we have some more descriptions and another code cell. How exciting. And this code cell, we're going to bring in data. What data are we bringing in? Prior to the class, I went here and I downloaded data, right? So I went to this table called B03002. I typed in to get this data for Los Angeles County, okay, at the census tract level. And once I have this data in, in the census reporter, it's still loading. I can actually download this data. Okay, so there it is. And when I download this data, I can download it as a geo. See, when I hover over the download data link, there's an option to download it as a GeoJSON. That's what we're going to use for our lab today. I can also download it as a CSV, KML, shapefile, the other data formats that I talked about earlier. But the GeoJSON is a single file that you can use immediately in Jupyter Notebooks. That's why I really like it. And it also comes with a metadata file. And we're going to talk a lot a bit about that as well. So going back here in your Jupyter Hub space, you'll notice a data folder here, right? Okay, so if you double click on the data folder, you will see that file from Census Reporter. This includes Hispanic and race origin data. And then you'll see a metadata file in there as well. Okay, go back to my presentation screen. All right, so let's bring in that data to our notebook. Downloading it and putting it in the Jupyter Hub, you can actually upload it to Jupyter Hub. If you have your own data, you can actually, if you have your own data from, any file explorer, you have your data somewhere here, you can actually drag your data, CSV file, an Excel spreadsheet directly into this space here, which will upload it to your Jupyter Hub space. Very cool. Okay, so when I execute this code, again, Shift Enter, hopefully it works for most of you, you'll notice again that you should have a new number in there. That's an increment from the previous cell. So my previous cell was number 4. Now I execute this code, it's now has number 5 in it. What did this cell do? It uses something called GPD. What is GPD? GPD comes from my previous code cell, right? When I imported Geopandas, I imported it and gave it an alias. So I said, I don't want to type Geopandas. I want it to be GPD, Geopandas for short. Contextili is CTX for short. Matplotlib is PLT for short. So we're going to use these acronyms in our code. So we're using the Geopandas library to read data. The Geopandas library has this function called read_file, which allows us to bring in data. Where is the data? I downloaded it and uploaded it into our data folder, right? So it's relative path to where this notebook is saved. So it's in the data folder / and a long file name, right? So this is where this data is. And what do I do with this data? I put it in a variable called GDF, which, maybe not the best name, but it stands for geodata frame is what we're going to put it in. So we're going to bring in the data and put it in a variable called GDF in a container. So now the data exists as a GeoJSON, and then we're going to bring it into our notebook, and it's now in a variable called GDF. Okay. So now what can we do with GDF? We can interrogate GDF. This is the data exploration phase, right? So we brought in the data. What does it look like? Can we actually open it in Python, in Jupyter Notebooks? That's what we're doing now. So when I do a command, and we're going to go through a series of commands, and these are all commands that, again, inspect the data in some way. So the first one I have is .shape. So what does .shape do? It gives me 2 numbers. The first number is the number of records that we have, number of rows. The second number is the number of columns. That's why it's called .shape. It's a shape of your data. How big is your data? How many rows and columns do you have? So we have 2,347 census tracts in LA County. That's good to know. It's a trivia question. And the data brought in 45 columns. That's a lot. I don't think we're going to need all of them. What else can we do that is fun? So now we can do another command, .head, and this time with brackets, parentheses in it. The parentheses are there because it can accept something called arguments. And I'll talk a little bit about that. But first of all, highlight that cell, execute that cell, and it should create an output immediately under that cell. Very reactive, very immediate, very satisfying, right? So now we have the first 5 rows displayed in your Jupyter Notebook from the data that was downloaded from the Census Reporter website. And this is what the data looks like. We have something called the GeoID. We have something maybe more human-friendly, name. So this is LA County, that first row, which is actually problematic. I'll explain later. And then we have a whole bunch of numbers. We have a whole bunch of headers that make absolutely no sense to us unless you work for the census. If you know what these numbers represent, I'm impressed. And this is the first 5 rows. Now, what does gdf.sample do? So I'm going to execute this second cell. And this produces a single row. And .sample is one of my favorites because it brings in a random row. So my output that you see on the screen here is most likely different from your output. You probably don't have the same census tract that I do. And if I run this cell, it says number 8 on it. If I run this cell again, I'm going to get a different census tract, a different random census tract. That's why I love .sample. I use it quite a lot. What are the parentheses? The parentheses allows you to add arguments and different calls. In this case, .head, which is a function. Different functions accept different kinds of arguments. So for example, if I said .head and I typed in the number 10 here, instead of the default 5 rows, it's going to give me 10 rows, right? So maybe you want to look at more rows. Maybe you only want to look at the first row, 1. It's only going to give me the very, very first row. Okay, so that's what the arguments are within the parentheses, and different functions will accept different kinds of arguments. So again, if you wanted to have 2 random samples, you would enter the number 2 there and execute the cell, and you'll get 2 different rows. Okay. Okay, so we can also plot this data. Plots and maps are beautiful, and that's why we're here, right? So let's plot this data. gdf.plot. What does this produce? So immediately it produces what looks like a map, which is pretty cool, right? So GDF, the geodata frame that we brought in from a GeoJSON file, recognizes immediately that this file is spatial. It has spatial elements embedded within the data. So it knows that if you say, hey, let's plot it, and notice the argument inside the parentheses here, it says, I want this figure size to be, 10, I don't know what these numbers represent. I think like DPI or some kind of size metric. I want it to be rather big, 10, 10. You can change these numbers if you wanted to make this map bigger. And then it defaults to a map. These numbers on the x-axis represents the longitude, right? And the numbers on the y-axis represents the latitude. So we know that LA, if any one of us are map nerds, we know that LA is about 34 degrees from the center of the Earth and north of the equator. So we're 34 degrees north of the equator. And from the prime meridian off the coast of Africa somewhere, if you go backwards from the equator, we are about negative 118 degrees from the prime meridian. So we're west of the prime meridian. And that's how geographic coordinates work, right? It's angular from the center of the Earth, north or south of the equator is for latitude, east or west from the prime meridian, 0 to 180 degrees. Pretty cool. All right. So let's plot a random row. What does that look like? Let me make this, I can see this, right? This is one of my favorite things to do, right? So like we have all this data. Every row, remember, represents a census tract. So what is this doing? We're saying, here's our geodata frame. Get me a sample, random sample, and plot it. Very cool, right? I can run this cell again and get a different random census tract in LA County. And I just love doing this. I'll just keep doing it over and over again. You can see the different shapes that represent our topography here in LA, right? And some of them are square, some of them have right angles. This might be somewhere in the mountains, right? It has all the curved edges. It's feels more mountainous and the north end here, and maybe kind of streets on the south end. You can speculate quite a lot just by looking at the shape of boundaries. Okay, I digress. Let's go back to our lesson here and talk about data types. So with any data, whether you're working in Excel, in a database, data types are important. So in Excel, if you have numbers in your cells and the numbers are consistent from top to bottom in that column, then you can right click on that column and create a chart because it recognizes that it's a numeric column. But if it has text in it, you can't create a numeric chart because it doesn't know how to interpret text. So that's why data types are important. So what is our GDF as a data type? So if I look at this and notice the new argument here, .info is what we're going to be using. It gives us information about our GDF, our geodata frame. What does it tell us? It tells us quite a lot. First of all, it tells us how many records we have, 2,347 entries. 0 to 2346. Most coding languages actually start with 0 instead of 1. So when you count in code, you don't count like 1, 2, 3, you count 0, 1, 2, 3. So that's 0 to 2, 3, 4, 6. How many columns do we have? Notice here, the count starts with 0. It starts with GeoID, and it tells us what type of data is GeoID. It tells us that it's a data type called object. Object is also a string. So think about object as a string, like it's text-based. And then most of our data is in a data format called float. Float is numeric, and unlike an integer, a whole number, it allows for decimal numbers, so decimal degrees. So all our data is pretty much float until we get to the last one, which is a geometry. And the geometry column is what allows us to map it. The geometry column is filled with GeoJSON code that we looked at earlier from Wikipedia. That's what this is populated with. And that's what allows us to actually plot it and make it look like a shape of a geography. Okay, so that's what our data looks like. And now let's talk about our first data column, which was GeoID. And this is one of the census assigned identifiers for geographies. It's consistent throughout the entire country. So whether your research is in LA, New York, Ohio, as long as it's within the United States, it's going to follow the same kind of identification procedure. They use something called a FIPS code. I forget what it stands for, Federal ID something. But the FIPS code looks like this. It's a number. It's numeric in a sense that identifies where that geography is. We're looking at census tract data, so we're at this level here. But the numbers actually start at the state level. So 0, 1 is probably Alaska, maybe the first. I think it's alphabetical. California is 0, 6. Right? So every county, census tract, block group in California will start with 0, 6. LA County is so counties are 3 digits, right? So states are 2 digits. We don't have more than 99 states, so it's 2 digits. Then it's followed by 3 digits, which represents counties. So there is no state in the United States that has more than 999 counties. The county of LA is 037. So 06037 is the FIPS code for LA County. I think there are 58 counties in California. So it will go from 06001 to 06058. And then the next, what is this? 1, 2, 3, 4, 6 digits represents the census tract. And if there's a number after that, that would be the block group. So you get the idea. That's the GeoID. So what does our GeoIDs look like? When I do this following cell, and you can hit Shift Enter on it as well, think about what this is doing. We're chaining a series of commands here. You can dot and chain commands, which makes Python very powerful. We're starting with our data, geodata frame. And then we're saying dot GeoID. What is that doing? Dot GeoID is saying, I only want to look at that one column GeoID. You can ignore the rest. And then I do a dot head. So we're familiar with the dot head, first 5 rows. So what this is doing is just showing us the first 5 rows of the GeoID column. And it looks like this. Remember that first one was a little different from the others. The first one, and by the way, we can start looking at these numbers for after the word US. What precedes the US is a different kind of identifier that we don't have to burden ourselves with at the moment. What we want to look at is what starts with a 06 here. So 06, 037, and so forth. That's state of California, LA County, and then the first census tract in LA County is 101110. That's pretty cool. Okay. How does visually, how does that get interpreted? So again, we start with the country. This is California, so that's 06. That's LA County, 037. That's a census tract in Boyle Heights. So that is the next 6 digits, right? And then that census tract gets subdivided and so on and so on. This is the geographic hierarchy that I talked about earlier. Okay, so that first row, that looks a little bit different than the other rows. What Census Reporter does is that it summarizes all the data and then puts it in the very first row. So that first row, since I asked for data for all of LA County, is actually LA County. But if we're going to produce statistics from our table, that row becomes problematic because it is different. So so if I look back at, okay, where's my data? Here, okay. This is LA County, right? And it looks different. Let me change this back from the other rows, right? And notice that first number here. So this variable I happen to know is total population. You guys know the total population of LA County? It's pretty big. In fact, it's 10 million big. So this number here represents how many people live in LA County, 10 million people. The next value is for a single census tract, 4,000 people. On average, a census tract anywhere in the country has about 4,000 to 5,000 people in it. So that's a good metric to know moving forward. So let me go back to that. So we need to delete that row is what I'm saying. So how do you delete data from a data frame? Essentially is what we're working in. So let's check our data again. So here's our gdf.head. We want to delete this row here that has an index, if you see on the left, with the number 0 in it. We want to get rid of that row. It's problematic. So there's code we can use to delete that first row. So this is how you do it. You drop. We're going to drop the 0th row, right? So we're going to drop, and then in square brackets, this is a list. Python square brackets represent lists. So I just want to drop one row, the 0 index row. And I'm going to redefine GDF to be one less row, okay? So when I run this cell and we check our head again, you should now see that that row has been deleted. Okay, so now everything is more consistent. Every census tract here is 4,000, 3,000, 6,000, right? It's about the average for every census tract. Okay, so let's do a bit more Python work to get us started. What do those wonky headers represent? Oh, okay. So I have a question. Is there a way to execute multiple cells at once? Not really. What you can do, Valerie, when you're writing your own code, is you can put as many things in a single cell as you want. So your entire Python code for all we care about could be in a single cell. And then you could execute a whole sequence of Python code in a single cell. I don't know if you want to do that, because there is benefits in chunking out your code so that you can run one after the other and the other, so that you can kind of troubleshoot and debug a little easier. But yes, that's possible if you wanted to do that. But the environment only allows you to execute one cell at a time. I hope that answers your question. Okay, so let's look at our data. Remember when I downloaded that data, it also comes with a metadata.json file. When I open this file, it looks like this. It might look a little different on your screen. I have a, what do I have? I have a plugin, a Chrome plugin called JSON View that allows it to kind of prettyfy, you know, the view of JSON code into what looks like it is on my screen. But this is what we downloaded. You'll notice here, there's that weird number in our header, this code, but this is what that represents, right? So 004, the one that ends with 004, represents non-Hispanic Black. 003 is non-Hispanic White, and so on, right? So we're gonna have to massage our data and do a little bit of work before we can begin to make sense of the data and map it. So let's think about this Python work that will go to get us to where we can finally map this data. So this is what our data is, right? So this is all the data variables that we're looking at. And notice how the data is indented. So we have non-Hispanic Latino here, and then it's indented for non-Hispanic White, non-Hispanic Black, and so on and so on. At the same level, we have Hispanic or Latino. So that tells me that Hispanic or Latino plus non-Hispanic or Latino is equal to the total population. And then there's further indentations here. So if you're Hispanic, what kind of Hispanic are you? You could be a white Hispanic, Black Hispanic, Asian Hispanic, and so forth. So it allows, if you identified yourself as Hispanic or Latino, you can further break yourself down into these other race categories. So that's what we're looking at. For the purposes of this lab, we're only going to look at the non-Hispanic Latino breakdown and the top level Hispanic numbers. So this way we can say, are you Hispanic or not? If you're not Hispanic, are you white, Black, Asian, and so forth? So that's what we're going to do here in this workshop. Okay, so we dropped a row, but let's drop columns. We have way too many columns. 45 columns is a little bit too much. So how do you drop columns? Dropping columns is a little bit different. Think about it the other way. Rather than dropping columns, what columns do you want to keep, right? And let's make a list of the columns that we want to keep and truncate everything else. All right, so that's what we're going to do. First of all, what are our columns? So when I do this function here, list, and then put our data frame in it, inside the arguments, what happens? It produces a list. So Python lists starts with a square bracket, and it will end with a square bracket. And it has comma separated values. So it's in JavaScript, this would be an array. But in Python, it's called a list. These are all our columns in list format, quite a lot, right? So we don't need all those columns. So what we can do is we can create a list of columns to keep. So I've done my homework. I looked at this table here, and I decided which one of these I wanted to keep. And I put the ones I wanted to keep in a list, right? So here's a square brackets. I want to keep GeoID for sure, right? I'll keep names so that it's human readable stuff. And these are those race categories that I highlighted in green, right? And then I definitely want to keep the geometry column because I want to map those census tracts. And then I put all this stuff in a variable called columns to keep. Okay, so then I run and execute this cell. I now have a variable called columns to keep. And what I can do now is truncate our data, our GDF, to only keep the columns we want. So this, what it's doing is taking GDF, our geodata frame, square brackets. What do we want to keep? The columns to keep. So I'm supplying it with only the columns I want. And then I'm redefining GDF to be equal just the columns I want to keep. Hopefully that makes sense. And if I execute this code and I run head on it again, you'll notice that my left to right scroll bar is a lot shorter now. Okay, so it only goes that much. I only have, how many was it? Like 8 columns now. Okay. All right. Any questions so far? I feel like I'm just kind of going rapid fire here, but maybe I'll pause, see if there's any questions. It's gone on for about an hour and a bit. All good?
I do have one question, Professor. Yeah. What does the errors mean? When we did the coding of the values, there were a lot of errors. What does that mean?
Yeah, that's the margin of error column that the census provides. It's a statistical error output that they give you along the actual numbers. So it's provided to you as a, for you to understand that those numbers come with some margin of error.
Perfect. Thank you.
Yeah. Okay, so I'll move on. So, okay, so now we have our data and we have those wonky headers that we don't want. Instead, we want human readable headers. So how do we rename columns? Okay, so first of all, what is our truncated columns? Now that our data has been cleaned up, we only have these variables, and this is what our data looks like. Okay, and we want to replace these values with something that's more human readable. All right, so how do we go about doing that? So essentially what we do is we can redefine column headers with a single argument, gdf.columns, and then feeding it a list of column headers. Now here's the thing. Notice how everything is comma separated. The number of values in this list has to equal exactly the number of values from the original list. You can't feed it more column headers than it has, in other words. So that's just one thing to make sure. When you rename column headers, make sure it has the exact same number of headers. Okay, so this is, again, this goes back. I looked at this list here. I copied and pasted these values and put it in our column headers. So I'm going to execute this code again, and I'm going to look at my data again. So now these headers make a lot more sense, right? It's pretty cool. When I see data like this, and this I encourage you as well, is to really kind of interrogate the data. You're responsible for your research. So I get nervous with data a lot. And I always want to make sure, first of all, that the headers are correct. Did I get this right? Do spot checks and so forth. So I'm looking at this data. So I'm looking at my first census tract here. There's that total number, 4,283 people live in this census tract. of which 3,000 are non-Hispanic. 1,188,000 are Hispanic. And I want to do a spot check here and make sure that these numbers add up to 4,283. So what I typically do is I'll bring up a calculator, right? Very old school, I know. And I will double check my math. So 1188 plus 3095 is 4283. So that's my spot check. And sure enough, that's the total there, 4283. Again, highly recommend that you do some kind of data integrity work when you get your data. We can do this programmatically as well. So let's see how we can do this with Python. So let's look at a random record. Okay. By now, this might actually make sense to you, right? Now that you're halfway through this Python workshop, right? So what am I doing? gdf.sample. We know that that creates a random record. And I'm putting that in a variable called random_tract. And then what's line 3 here doing is that it's actually outputting it for us to see it under the cell, random tract. Your random tract is going to look different from my random tract, right? So what you see on my screen is probably not the same as you see on your screen. Even just looking at this, I can almost immediately tell what kind of census tract this is. Because look at this, there's 2,000 people in it, so there's fewer people than the average. Almost all of them are non-Hispanic, right? There's only 264 Hispanics living in this census tract. So visually, and knowing LA, I've lived in LA for more than 20 years, I can kind of speculate several places that this census tract might be in. Okay, and yours will be different, of course. Okay, so we're going to look at how to get to different values in the data frame, and we're going to use a command called iloc. Let me explain this through the actual code. So what I'm going to do is I'm going to output a number using the iloc command. The iloc command is a little bit more complicated, but we're looking at a random tract. Okay, so our random tract only has one record. So what iloc does is says, let's locate a value with an index number of 0 from your data, in this case, random tract. And let's output the total of that random tract. So I just want to know what the total is. Again, your number is going to be different from mine. In my census tract, 2,070 people are living in it. What else can we do with this? We can actually output some kind of human readable contextual material. So in this case, this is another function called print, where we can actually combine text in single brackets, right, with actual code values that we're going to produce. This might look a little bit complicated. There's a lot of things happening here. But when I execute this, I just want to show you the output. It shows me the same thing as what's above here, but I've added the word total population so that it's kind of more explainable when you look at it. And I can do different like print commands to, for example, output this string here, non-Hispanic plus Hispanic is equal to this number here. And I'm actually doing the math within the print command. Let's not worry too much about this for now. These are just kind of spot checks that I've just put in for your reference. And whether or not this is my census tract or your census tract, every output here, the point being, should be the same. And this is the spot check that I've done for my own work. Because this is how the data is or should be aggregated. Okay. Okay, so the data integrity work may be overdone, but highly recommended. Let's move on. Let's now build some stats and plots. So once again, let's look at our, let's get away from a random track, go back to our GDF. You'll notice a different notation here. I have GDF, square brackets, and in single quotes, the header name for total. This is another thing about Python, is that there's usually many different ways to do the same thing. So I'm introducing you several different ways to do the same thing. So this gives me the first 5 rows of the column header for total. I could do the same thing with the other notation, which was this, right? Without the square brackets and the single quote. This seems a lot easier, but there are reasons sometimes when you have to use this notation, and that is whenever your header, whatever your header is, has special characters or spaces in it, you have to use this notation. You have to use the square brackets and single quotes. So I hope that makes sense, and I hope that makes sense of why I'm bringing up different ways to do the same thing. Okay. All right. So now we know how to get values from individual columns. What about average? What's the mean of that entire column? In other words, what is the average population for every census tract in Los Angeles? If you added all those up and divided by the total number, what does that give you? 4,297. So that is the average number of people who live in every census tract in LA. What is the median? 4211. So the median being the 50th percentile. If you were to divide up all the census tracts and sort it by population and grab that middle census tract, that's that value there. It's almost equal to the mean, right? Getting some statistics with dot describe. What does this give you? It gives you kind of a larger summary. How many records are we looking at? 2, 3, 4, 6. That hasn't changed. What is the mean? That's the same as what's up here. And then the standard deviation. And here's the median, right? The median essentially is the 50th percentile. So that number is equal to that. Other things that are useful to know. There are census tracts in LA that have no people in it. So there's one with 0 people. What is the highest number of people who live in a census tract in LA? It's that max number here. So the largest, most populated census tract in LA has 12,000 people in it. Right? Okay, so let's create our first plot. Finally, all that work. And I know we spent, how long did we spend on this? 45 minutes. And just looking at data. This is about right. Whenever you work with data and you want to map data, expect to spend 75% of your time at that data level. Like, what is this data? What does it look like? What columns are there? What columns do I need? Do I need to aggregate data? Do I need to create new columns, et cetera, before you actually get to work with the data? Okay. So let's create some simple plots. This is a histogram. And oh, sorry, that number 50 was not in there. So there's a default number, maybe it's 10. What I want you to do is in the argument for the histogram, type in the word 50 or the number 50. And is that right? Ah, let me see. 100? That doesn't change, huh? CDF total plot. Okay. That looks different than what I was expecting. But I wonder, is your output the same as mine? Okay. So for whatever reason, what I'm expecting is that I have 50 bins across my distribution here. Okay, something got wonky, but it's still producing a histogram of the data. It tells me that distribution of population in all the census tracts in our data actually looks kind of like a bell curve here. I can further supply arguments to this plot here. And notice that it's still the same thing. It's got the parentheses in the outsides here after the plot.histogram, but I'm saying I want it bigger. So I'm providing a bigger fig size. You can play with those numbers. This is the one that, for whatever reason, wasn't working in my previous cell. Did I type it wrong? Bins. Yeah. Okay. Bins is equal to 100. So it breaks down my data in larger chunks, and I give it a title, right? So LA County Census Tracts by population size, ACS 2019 5-year. This is the source of the data. This is pretty cool. I can publish this in a research paper. This is the distribution of population in census tracts in LA County. And maybe I have the same distribution for a different city that I want to do a comparative study on. That would be very informative. Okay. So moving on, maybe I'll pause here again to ask for questions. If you wanted to kind of play with this a little bit, see if you can maybe change that total field to something different and see the distribution, or use the next couple of minutes to take a quick break or ask me any questions. So I'll pause here for a few minutes. Anybody have any questions so far? All good. How is everything? Everything's working? Is the pace okay? Yeah. Okay. I'm gonna take oh, thank you, Johanna. I'm gonna take the silence in the chat room to be a positive thing. Okay, thanks. All right, so moving forward, let's do a couple more things with this data that is probably very useful for, you know, when you bring in your own data, you're going to want to know how to do these things. Sorting data. So once you have data in your notebook, how do you sort it? So there is a, I have a link here for the documentation. There is another function to sort data called sort_values. So it's GDF is our original data set, and you can sort values and provide it arguments. So in this case, what do you want to sort it by? So you give it the column name you want to sort it by in single quotes, and you want it to be ascending, true or false. Ascending false means that it's going to give us the highest number first and then the lowest numbers last. And then I'm going to put all this in a new variable called GDF sorted. Okay. So let me go ahead and do that. And let's look at the data. And every time I run a new cell, I introduce a new concept. So let me explain a few things here. Again, we're chaining a few things here. GDF sorted is our newly sorted data frame. We created it with sort_values by total population, right? But what am I doing here? I'm feeding it in square brackets a list of 2 column headers, and then ending the square bracket outside of it. And then I'm getting the first 10 rows. So all that work happening in one line of code, if that hopefully makes sense. What this is doing is, you know what, I don't want the entire, you know, spectrum of my data. I just want to see 2 columns. So maybe I want to plug this into a report or something, and I only want those 2 columns to show and not everything else. This is how you do it. You get the data frame, and then you list the column headers that you want, and then you create the output. So this could be plugged into report as well, and this could be the title of this could be top 10 census tracts in LA County in terms of population, right? And these are the GeoID, and these are the numbers that we're looking at. We can plot this. Okay, so what happens if we just do the plot command, right? Remember, every row comes with a geometry column. The can actually draw the shape of that census tract on the coordinate system that we're on. It's beautiful, right? So each one of these plots are drawn visually for us to see in the latitude and longitude space that we've created with the dot plot command. Now, have fun with this. What if you change this number, right? What if I change this to 100? What do you think it's going to do? It's going to produce the top 100 most populated census tracts in LA County. I was kind of surprised by this. I thought there would be clusters that were more recognizable, but it does seem pretty dispersed and kind of all over the place in terms of very highly populated census tracts. Okay. All right. So let's think of other arguments we can feed this plot. Let's map 1,000. So it's roughly a third of all the census tracts, a little bit more than a third of all the census tracts plotted. And then we're adding a few arguments here. Okay. So what is this going to do? This actually output may not make any sense at all, and it's probably not publishable, but just wanted to introduce a few things. Column argument inside the parentheses for plot automatically colors the census tracts by a value. This CMAP thing, that's a color, what's it called? A color palette, right? That's reserved. This is a reserved word. The plasma palette goes from like, dark blue to bright yellow, and it's a spectrum between those two colors, and it assigns a different color for each census tract that you're feeding it. Okay. In the interest of time, I'm going to skip this now. It's your turn. So I'm going to move straight on to another segment. So now we're going to filter and subset the data, querying data. This is really, really important because you might have your entire data set, but your research question is typically not going to be about your whole data set. You're going to want to ask questions like, well, where do the top 10% of Hispanic population census tracts, where are they? Where do they live? And so forth. Or what are census tracts that are 80% or more African American? That might be important for your research, identifying locations of places based on a query. So let's do a simple one. So what if we wanted to query, remember there are a whole bunch of census tracts which had no people in it. So where are these census tracts? So this is, an example of how to do that. Again, we start with GDF, which is our data, square brackets. Within the square brackets, you can feed it the query, right? So that square bracket notation is very powerful. You can either feed it columns to only show separate columns, or you can actually feed it a query to filter the data. So in this case, we're saying, oh, you know what? Only show me data where the total is equal to 0. Okay, and that produces this output. So you'll notice here that everything is zeros all the way down. 0, 0, 0. In the very bottom, no, it doesn't. Okay. And we can put it in a variable, right? It's the same thing. I'm just going to create a new variable, GDF _ no _ pop. Okay, so we're going to put it in a variable. And again, we can use the print command to kind of chain a human readable output. So how many census tracts are there with no people in them? Again, these are things that I haven't specifically talked about in length, but in order to get the number of records, you do the LEN, which stands for length, and that gives you the size of that data frame in terms of the number of records. Okay. And we can display it in this way, right? So again, GDF no pop, and we can actually output all those census tracts in table format. Okay. All right. So the next step I want to talk about is normalizing data. So this is maybe something you will do with your own research as well, is you'll find out that total numbers are not always representing what you want to map. And it's actually the percent of total that is more relevant. So case in point, if you have a census tract with 1,000 Hispanics in it, another census tract with only 100 Hispanics in it, which one has a higher proportion of Hispanics, right? You would tend to think it's the one with the higher number, but not necessarily. If that census tract had a whole bunch of people living in it, it may only be 10% Hispanic. The one with 100 people living in it may only have 100 people in it, it will be 100% Hispanic. So that's why we want to normalize data. So let's figure out how to do that. First of all, I'm going to output our columns. These are the columns that we've chosen. And in order to normalize it, it's simple math. So percent non-Hispanic, we would have to take percent non-Hispanic and divide it by the total and multiply it by 100. So we can do that programmatically. So each one of these produces a new column in our data frame, right? And normalizes our data. So let me explain how I did one of these. So here's GDF, our data. And then in square brackets, I have a string of text for something that doesn't exist in that data frame. Does that make sense? So when Python sees this, it says, oh, you know what? Percent non-Hispanic doesn't exist. I'm going to create it for you. So it creates a new column. And you're also giving it a value, a dynamic value. So you're saying, I want that column. I want you to create that column and calculate it based on non-Hispanic divided by the total, and then multiply it by 100. And then I repeat that for all the different columns in the data. So what this does then is it produces, as you will see here, if I scroll to the right here, it produces all my percent columns here. And again, if I had time, I would do spot checks on this, but you know, here's percent non-Hispanic is 24%, for example, and percent Hispanic right next to it is 75%. These two numbers should add up to 100, and they do, right? So these numbers are different from the total numbers, which will produce more relevant and research valid, peer reviewable maps. Okay, so finally, in our last 10 minutes or so, we're finally going to get to some cool maps. All right, so let's talk about maps. How can we create choropleth maps in Geopandas? I have a link here to the documentation for creating maps using the Geopandas tool. And you know, this is great. They have sample code here, and then the output below it. Same as our Jupyter Notebook. I mean, this looks like a Jupyter Notebook, right? Sample code, the output. Sample code, the output. This is what we're going to do with our data, pretty much, is producing these choropleth maps. Okay. We're also going to use color schemes. We're going to do something. We're going to classify our data. Like, why is a certain census tract a certain color? It's because you told it to be that color. How do you tell it to be that color? Those are called schemes, and we're going to classify data differently to produce different kinds of maps. Okay, so you know, with just that amount of code, gdf.plot, and then you give it a size for that plot. Remember the column, we're saying you want it to be percent Hispanic. I'm giving it a legend, setting legend to be true. And I'm giving it a scheme, which is the classification of the data, to be equal interval. And that produces a beautiful output, isn't it? Right? So here's our map. We have, it's mapped by percent Hispanic. The legend shows up here on the top right. And the scheme is equal interval. Right? So I can do the same thing, right? And do the scheme to be different. We're going to use quantiles, right? And in this map, it looks almost identical to the equal interval, but if you were to zoom in, if you had the capability of doing that, then you would notice that there were some slight differences there. And look at the breakdown, right? The breakdowns are different. Quantiles ensures that your map looks visually stunning, because it essentially what a quantile does is that it says, you know what? I'm going to put equal number of census tracts in each one of these bins. That's what a quantile does. So it'll have equal number of yellows as opposed to blues, as opposed to these teal green colors. And the last one is that you can define your own breakdowns. So this map actually, I think, is the same as equal intervals, but you could change this however way you want to, right? So if I only wanted 3 colors broken down a certain way, I can produce an entirely different kind of map. So this is where you as a researcher say, you know, what's important for my research is to find out where, you know, certain population groups exist and where others don't at a certain threshold. So you can create very customized, very meaningful maps just by changing these numbers. Okay. I'm going to end with kind of a little bit more advanced plots. And this might kind of go over your head a little bit, but the fact that the code remains here for you to play with later, I think will be a good thing. So let me just kind of get out of this mode here so I can see the whole code. It's a lot of code. You know, someone asked me if you can put a lot of code in a single cell. This is an example of that. What this is going to do is we're going to do side-by-side plots. So rather than one plot after the other, we can actually create side-by-side plots. And again, the syntax is a lot more complicated. We're using something called, this is the matplotlib library, which is a little higher level library than GeoPandas. So we do plot, and then we're creating subplots. And we're saying, I want a 1 column and 2 rows. In other words, side-by-side plots, essentially. And we give it a fixed size, right? And this creates, you know, first plot on the left, second plot on the right. How do I want to define my plot on the left? Is that first chunk of code that I've highlighted here. How does it know it belongs to the left? I give it the argument to put this map in the left. And then down here, this is the output for my second map that is assigned to the second plot on the right. Again, complicated syntax. All this code produces the map that introduced our workshop, right? This is the graphic that was in my repo. And this is a very powerful map, actually, right? So it takes census data from ACS, American Community Survey, 5-year estimates, 2019. And it brings in % Hispanic data. And if you know our city, you'll know that this makes sense, right? South LA and the area Southeast LA has a high number of % Hispanic, represented by the red. 80% or more people in these red census tracts are Hispanic. On the flip side, African American, Black populations. I live in Culver City. Culver City is highly the south side of Culver City, which makes sense, right? Has a high number of African Americans into Inglewood. So these two maps, to me, as someone who's lived in LA for a long time, make a lot of sense to me. Okay. I am actually going to pause. You know what? Let me just kind of finish this out. This is kind of optional stuff, but I'm going to well, let's go through, since we actually do have another 8 minutes or so. This might actually be more relevant for many of you, is that you actually want to specifically map certain population groups. And this is where the ability to query data is very powerful. And we kind of explained this earlier, how to query data. And I'm just kind of reiterating this. So if we wanted to see, the research question might be, where do census tracts with people, Hispanics, with 80% or more Hispanics live? Where is that in LA County? First of all, you would query your data, so it produces only the census tracts that match that query, right? That is greater than 80% Hispanic. And then once you have that, you can plot it, right? So now we can plot it, and it produces a map of that query, essentially. And you can change these numbers, which is great, 90%, 80%, 70%, to produce very meaningful maps for your inquiry. The last part of it is to produce a base map. So in just a few minutes, the base map, we're going to use a library called Context Tilly. And that library requires you to reproject your data into a coordinate system called Web Mercator. It's a long story. Base maps are essentially images that have been pre-baked. And when images for maps are pre-baked, that means it assumes a certain coordinate system that's not dynamic. You can't change it on the fly. And so since they use this coordinate system on the right, which is Mercator, we're using latitude, longitude, which is geographic and angular measurements. We have to convert our data first. So long story short, this cell here converts our data to Mercator, right? So now our data is in Web Mercator. And let's just scroll down to the bottom here. And when you produce a map in Mercator, you can then add, here's line 14, a base map from Context Tilly, which allows you to produce a map that looks like this. Yes, thank you, Jennifer. And that is pretty cool, right? So this is in the blue, shades of where 50% or more of the people living in these areas are Hispanic. And again, the beauty of a Jupyter Notebook is that you can come right in here and change these numbers on the fly. So if I wanted this to be 80 instead of 50, I just change that here and I made that 580. That's not true. Okay. And it gives me a different map, right? So I can then have maybe multiple maps on my report that produces different outputs. Okay. I think that kind of wraps it up for me. Thank you for surviving this long 2-hour session. I hope it was useful to you. If you're still around, if you could fill out this survey, that would be great. I'll send out an email with everything in there, but I'll also be sending out a link to everything from the workshop to all of you guys, along with a link to the recording of the workshop, and also a link to my office hours. So hopefully I can see you guys during my office hours. What I'm going to do now is I'm going to stop the recording, and